some rest soon. And I may just end up finishing work, just falling asleep today.
I don't know, and then like allergies are starting.
Oh yeah, mine get bad and stay bad all the time. Well, it's most notable in spring, I'll admit that. But I feel like they've been legitimately getting worse in recent years, to the point where I'm taking allergy pills year round, and now that I'm in spring, it's even worse. Yeah.
Well, I didn't used to have it until like 2 years ago.
I'm here. Maybe the pollen is just getting exponentially more toxic. Nature's fighting back. Machines are rising up, the trees are rising up. Cats have always hated us. What's next?
Well, usually like I had to get allergy shots a while back. I got them like for 5 times because my allergies are so bad.
Oops.
And they've since I've stopped now, they've gotten worse. Because I was ready, but I wasn't. So, but like mold can actually be a big one too.
Oh, yeah, our swimming pool in high school had a lot of mold. And like, I mean, I was a swimmer, so every day we would be exposed and like, I mean, the floor was green. Yeah. Yeah, and so we were like dying, we were all stuffy, and we couldn't breathe, and we're doing these hard sets, and we had to get out and be like, yeah.
That literally should be,
Illegal.
again, illegal against all kinds of regulations, exposing students to that knowingly. I don't care if you're out of money, that gets fixed. It was summer of 2013. I was on PC campus doing research, and it was like the wettest and hottest summer on record, which combined meant that most buildings were full of mold by fall. And so the school went on a whole semester-long purge. They found the buildings that were completely free of mold and moved people into those as the other ones were being cleaned out. And it was just a strategic floor-by-floor elimination. Sucks that it happened, but that's
Where did you
closer to
live?
the kind of response I would have hoped for from your school.
And when you went to PC, where did you live?
Most of Georgia Hall. Georgia 4th floor, Georgia 3rd floor. I forget the name of the other building I lived in. It's one of the dorms next to the international school. But then my 4th year, I came back and went to
Wait, next to it? I thought it was the all-girls building, the Groton's one.
No, it wasn't Grotness.
If it's in front, it was Bradley. What's the company?
Spradley? Maybe.
Or Barron.
Barron.
I don't know where that is.
I lived in Barron.
Yeah, that one's right beside Sarah's.
That's what I meant.
Beside what?
Like the international house.
Yeah, the last building on the edge of campus where you have the gym and the fields. Okay, I hope everyone gets sleep. I hope allergy relief is soon at hand. Speaking of relief from things, I've been getting some questions about homework over the weekend. So I want us to spend as much time as we need looking at chapter 15 stuff today before we move on to anything new. So, as you guys were working through those, is there anything specific that you've encountered that you'd like to talk about?
Number 4. Can you draw it? I think that's what I can't get.
Okay, yes. So, number 4, and I've also been asked about number 6, so we can look at that one too if you guys like. But to start with, number 4. This is a very interesting situation, so yes, let's draw a picture together. An airplane is flying through a thundercloud, at a height of 2,300 meters. So from the beginning, we have the Earth here, then the airplane. This is a very poorly drawn jet.
That's good though.
Very poorly drawn, but surprisingly happy jet at a known height above the ground. So your distances will vary on this one, but this is a known height. We know the plane is this high and that it is flying through storm clouds at that particular height. Problem goes on to tell us that this is usually a very dangerous thing to do. Then it says if there are charge concentrations of plus 40 coulombs at a height of another known height within the cloud. So this is at a different height from the Earth still. So we're going to draw up from the Earth into the sky. This drawing won't be to scale, fair warning.
But like, is this all within the same cloud? So that means that it was vertically in line?
Yes. I like using red and blue for positive and negative charges, so one of these clouds is going to be red. So the way I'm going to draw this is, the plane is at this height. There's a positively charged cloud above it at this height. And then it says there's a second cloud with a charge of negative 40 coulombs at a height of 1,000 meters. So this is our third height in this problem. So I'm labeling these as height of plane, height of the 40 coulomb cloud, height of the minus 40 coulomb cloud. So we know all of their distances from the ground. From this, we can extrapolate the distance between cloud and plane, and then plane and, sorry, negative cloud and plane, and also from plane to positive cloud. So every number given so far has been a height from the ground to their respective object. We also know the charge of each of these clouds, negative 40 coulombs, positive 40 coulombs. And we are asked, what is the electric field at the aircraft? Give magnitude and direction. So, we are going to assume, for simplicity's sake, this plane is sandwiched directly between these two clouds. Since the positive charge is directly above the plane, what direction is the field given off by this plane, by this cloud, going to be with relationship to the plane? Straight down. Very good. Positives emit field out of themselves. So that vector is going to point downwards. Meanwhile, the negative cloud is beneath the plane. Negatives, we say, tend to pull field into themselves. So its vectors are also going to point down. So each cloud is separately going to give off its own E field. So total E field field acting on the plane will be equal to E field of positive 40 Coulomb cloud at the plane's location and the E field of the negative 40 Coulomb cloud at the plane's location. Those are going to add up to something. Each field is being produced separately, but they are both traveling to the spot of the plane, and because they're vectors, they're going to add up. Without doing any math, what direction is the total E field going to point at the plane's location? Downwards. Both clouds are separately creating fields that point down at the plane's location, so a negative plus a negative is even more negative in terms of direction. So that, before doing any other math, can tell us this part of the answer. As for the actual magnitude, however, we are going to have to figure out each of these E fields separately and then add them together. So I've got two fields here listed. Sorry for my handwriting and for the distance. This is the E field produced by the positive cloud at the plane's location. This is the E field for the negative cloud at the plane's location. What is the formula for E field?
K times Q source over R squared.
Very good. Field is K, Q source over R squared. We have two fields, so we need to look at both of them separately. Total field acting at the plane equal to E field from the 40 cloud. I'm just going to go ahead and plug the formula into this spot. We will have K times Q over the positive cloud. I'll go ahead and put in positive 40 coulombs. Divided by the radius between plane and positive cloud. Your numbers will vary, but since the plane, for these numbers, plane is at 2,300 meters, 2,300 meters, and the positive cloud is at 3,650 meters, the distance between them will be the difference between those two numbers. So for mine up here, I will write out 3650 minus 2300. Very good, thank you. Square.
Wait, really quick, we know that we're adding them because they're both going down.
Yes. Which is why the picture is handy. We know that they are both pointing downwards.
So the charge does not matter in vector or whatever, yes.
The direction of the field matters. Absolutely.
But not like the negative or the positive that you get from the map.
Correct.
Yeah. Okay.
There is and you can put as an asterisk in your notes, there is a disconnect between signs in charge versus signs in E field position. Because the clouds have opposite charges, but because of where the plane is between them, both of their fields are pointing down at that location. So that does create a disconnect because you would normally plug a negative Q into here and a positive Q into here, and those would normally work against each other. going to actually add absolute value signs around our two pieces, our two E field calculations. Because if we don't, this one will be a negative number being added to a positive number. Yes?
If it didn't ask magnitude and direction separately, would your answer be them added but a negative number?
Potentially.
Like, I guess going with like the normal coordinate system, that like up is positive and right is positive, like that?
Yes. That said, I prefer, and I like that WebAssign does ask you to specify. I will admit, the biggest headache with these types of questions is the signs and the field correction. That's why pictures are kind of a requirement. Working this one to get the correct answer, we do want to add the two E fields together, but we have to know from the picture, regardless of which cloud made which line, they're both pointing down. Therefore, they will add together linearly and not work against one another, which is where the absolute values came from, so that it cancels out any negatives inherent to the negatively charged cloud. Any questions about this one? Excuse me. I'm glad you asked about this one because it sets up something that I'm hoping to introduce by the end of the period. Real quick.
Can we go over that one too?
Yes. This is the one I've got questions about, so I wanted to address it. So, if I haven't mentioned it yet, the term Van de Graaff generator is, I don't have that slideshow open. In some of your previous science classes, especially when you were maybe in middle school, the teacher may have had a machine that when it was turned on, there was a metal ball that you would touch and your hair would probably start standing on end. It built up a charge and you had a charge. It just kind of looks like a metal ball on a stick attached to a generator. Wait, I have the internet. I can just find you a picture. These things. So,
Are they normally that big?
they can be. If they were, it would just take them longer to build up the charge. But they can be. There are some in the building that are mostly open, that are about this big. Either that one is very large or it's a very small child, possibly both.
Can a charge like that lift you or not?
Lift a human?
Yeah.
See, the scary, for that to actually work, the human would need a net charge to remain in their body, which you'd have to be either positive or negative, neither of which is preferable, you want to be neutral, typically speaking. You want all your protons and electrons balanced, but you would also need a very big charge differential to actually have an electric force act on your body and that you could feel. And it would have to be a very big force generated to actually lift you off the ground.
So would you die?
Potentially, because you would either have to have a lot of electrons added to your body or taken away from your body, neither of which are a good thing. And if in this condition you touch the wrong thing, you will get zapped. Because either your excess electrons will leave or you will gain electrons because you're positively charged from whatever you're touching.
Wait, do you use that because it's negative, negative, or positive, positive?
Electricity always goes from negative to positive. So if I was negatively charged and I touched something, electrons would leave me. If I was positively charged, I would touch something and electrons would enter me. Either one hurts because your nerve endings can't tell the difference. Kind of like when you feel temperature. You can tell what direction it's going in, but it still hurts either way. Electricity, you can't tell what direction it's moving in.
You just feel like shocked?
Yes.
So like if every time you're shocked, either electrons are entering or protons. No, protons are entering and electrons are exiting.
Either electrons are leaving or electrons are entering. Your protons shouldn't be leaving your body
Why?
because they're stuck in the nuclei of your atoms.
I don't know.
We call it electricity because it's moving electrons. Although arguably the word electricity came before the word electron. So 6 to 1, that goes together. Okay, so that's what this machine in the example is. That's not the point of the example, just to paint that picture. So that type of generator is charged so that that's the ball, that's the orb at the top of the machine. We have a proton right next to it. This object is charged such that this proton placed next to it is about to be slingshotted out in this direction. So if you put a proton next to something and the proton runs away, what type of charge should this thing have?
Positive.
Very good. We know that this generator is positively charged. It has some positive charge to make this happen. We are told that this electron accelerates away at this acceleration. We know a few things about protons that can be handy here. So from our notes, the list of constant things that are always the same about protons. Mass is going to be, this is the number I always have trouble remembering. Mass of a single proton in kilograms. So we use kilograms more often here. It's going to be 1.67 times 10 to the negative 27th. And charge of a proton. Wait, no, it's there. Charge of a proton, 1.6 times 10 to the negative 19th coulombs. Because this is a proton, we automatically know these two numbers about it. We are then told the rate at which it's going to accelerate away from the orb. So, we know particle mass, we know particle acceleration. we are asked in part A, what is the force causing this to happen? What is the force being exerted on the proton to rocket it away? And I'll just list in the corner. We do know mass, we do know acceleration, we are asked for force.
Should we use F equals MA?
Yep. That formula will never not be useful. Force equals mass times acceleration. Because every single electric force we've calculated is a normal force. It is just a force that makes masses accelerate. So, proton mass times whatever your acceleration is should tell you force in newtons. And all we know for certain is the proton's being pushed away, therefore the force must push away outwards from the orb. Questions so far?
Should we do the second one? Was that when you would use the charge?
Yes. So, part A first, I recommend submitting your answer, making sure it's correct. Once you have this correct number, now we look at part B. What is the magnitude and direction of the electric field on the surface of the generator? And this would be the electric field that exerts the electric force on the proton. So since the orb is positively charged, its exerting field out of itself.
But like, if the proton is there, doesn't it go the other way?
Well, orb is positive, proton is positive.
Yeah, so don't they go like,
Yes. They are going to repel. Proton moves this way. The orb has a much bigger mass, so the same force isn't going to make it move very much. But the same force is applied to both. The reason that there's a force on this particle is because the orb is positively charged. It's exerting positive field out from itself. The proton is in that field that creates the electric force. So we know that this is about electric fields. You're asked specifically what the field strength is. So we're going to look at our formulas for electric field. A second ago, we used K, Q, source over R squared to tell us electric field. Will this be useful in this scenario with what we know and what we don't know? A little louder, sorry.
no?
No. In this specific situation, we don't really know the distance between the proton and the orb, or the proton at the center of the orb. We also don't know the orb's charge. Since the orb is making the field, it would be the source in this case. So this version of the formula is out, but it has a different version. It's not one we've used super often together, but the full formula for electric field had a middle step. E field is equal to KQ over R squared, but it's also equal to electric force divided by test charge. This part of the formula here that we've used more often, this is how you calculate the field given off a certain distance from a known source. In this situation, we aren't really describing things in terms of the source. We're describing things in terms of what happens to this proton, which is just in the other object's field. Which is why we can use this piece to analyze it. This part of the formula here is about what happens to something in a field made by the source. So this piece is made by the source. This piece is what happens to things in the field the source made. So this tells us electric field is equal to the force that acts on a particle divided by the charge of that particle. As long as this particle is in the field, there will be a force on it depending on the field strength and its charge.
And the test is the proton.
Correct. From the perspective of the orb's charge is producing a field. We have put the proton in that field, which makes the proton a test charge. So we take the force you calculated in part A is the electric force acting upon the proton. You take that number, you divide it by the charge of your proton, and that will tell you the strength of the E field that is doing this. And there's a hair stuck in my glasses, sorry. Excuse me. Does that not make sense to anybody? I want to ask you from that perspective. Okay. This particular assignment is a lot of the same principles repeated, but in different situations, in different types of questions. So, even if it's the same formulas over and over again, each scenario is subtly different in ways that are hard to generalize if we're not looking at that specific question. Yes?
So the direction for B is radially, whatever, outward because,
outward from the orb.
and outward from the proton.
The proton would be exerting its own field out from itself.
That's A,
Yes.
right?
No. All of the answers for this question have been from the perspective of the orb.
That's just the same like question. Right?
It's the same direction for both.
Because it's from the,
Right. The orb is exerting field radially outward. It's going to exert a force on a positive charge radially outward and repel positives away from itself. If we popped an electron here instead, the answer would be radially inward.
for both.
Yes, for both. Well, no, actually.
Because I thought A was talking about the proton, that's why I thought.
Correct. Okay, sorry. Yes, actually, A is from the perspective of the proton. It's being blasted away, so the force on it is outward. This answer is from the perspective of the orb. So, regardless of what test charge we put there, the orb is exerting field out from itself because it's positive. In this specific situation, because it's a positive acting on a positive, fields are being exerted outwards and forces are being repelled outwards.
I understand 7A, like that you use F equals KX, right? But I don't understand 7B.
Okay. So 7 is a combo problem. We're bringing back some old some of the spring rules and elastic potential energy rules from 1500. This problem is about balancing forces. So I'm going to roll the screen up so that I can question. So 7 tells us about a vertical spring. The spring has a known spring constant and a certain mass of object is hanging from it. So the picture I'm going to draw, this is the ceiling, the spring is hanging from, and there's some object hanging from that spring. So this is how I would draw the situation. We know the spring constant of that spring. We know the mass that is hanging from it. Numbers will vary. And part A is just a classic spring elasticity question. In this situation, there's a force being applied downward on the spring. The spring is going to stretch until it reaches its equilibrium position. Anyone need to review that further?
So are you looking for X?
Correct. It asks the distance that the spring needs to stretch so that it's in the equilibrium position. And from this mass's perspective, I'm going to go ahead and say this is force spring. From the mass's perspective, some of the forces should be its own weight plus the spring force equals 0. Gravity is pulling down, the spring is pushing up. I should actually draw and label those. So in part A, there's only those two forces involved. We know that the force, the spring force, needs to be equal and opposite to the weight. We plug in that weight for F spring. We know K. We can solve for distance stretch. This is before any electrical stuff begins. Or B, we're taking the same situation and adding electric force. So same situation, similar drawing, but I'm going to make a new one. In this situation, the mass not only has mass, now it also has a charge. So whatever its mass was is staying the same. But now it also has a known charge as well. Most things with mass also, most things with charge also have mass. So it's the same object, we just removed some electrons from it. And same spring, same planet, but now that it is charged, we're also going to add an electric field directed upwards at this object.
Whoa, why? If it's positive. Oh, wait, it says the electric field upward is applied. Oh.
Yes, so the object is positive. We are told positive charge. We're also told that separate from that fact, an electric field is now being directly upward at this object, being directed upwards straight at this object. And you are told how strong that field is. So you do know field strength. You know, charge and field strength. In this situation, you are asked then, what is the new equilibrium position? So previously, we had two forces balancing. What is different now? We've added a third force. Since the mass has a charge and is in an electric field, the electric force is also going to push on the object. What direction will the electric force be pushing? Straight up. Very good. So,
take this same line and rewrite it here for the new situation. Net force acting on the mass, we've got gravity down, spring force up, and now electric force up. And they all still need to add up to 0. But gravity is the same because it's the same mass on the same planet. So gravity is going to be the same number. What's going to change is, since there's this added force pushing upwards, the spring no longer has to push as much. So the object will shift upwards slightly, and the spring will have a new equilibrium position.
Wait, why do we know equal 0?
I am directly telling you, since the problem doesn't specifically say these words exactly, I'm telling you that in this, after this charge and E field are applied, the object will slowly shift upwards a tiny bit and then stop. It's just going to levitate there and it's a new equilibrium position. The question then becomes, find the new reduced stretch length of the spring. And this principle here is still the same. Spring force is equal to Kx. The only difference is the spring force is no longer equal and opposite only to gravity. It now has to oppose the sum of gravity and electric force. So, my recommended order of operations: first, use this line to solve for spring force. You want to get spring force equals blank. It's going to be a lower number than it was before because electric force is opposing gravity. So this spring force will be a smaller number than what you found up here. Step 2 is plug that spring force in here and solve for x.
So to find FE in the first step, are you going to use, which formula for FE are you
It's a very good question. We are told the charge of the object and the field that that object is now surrounded by, which more closely resembles this half of the formula. We know the E field, we know the charge of the object in the E field, we want to know the force the field exerts on it. All right, sorry.
So we use the E equals F over
Correct. Draw blue lines here for that.
to get force.
Yes. So use this to find the electric force that you will plug into here. You know what? I guess that's actually step 1. I'm going to call that step 0. So you don't have to change your notes.
Why is it equal to negative Kx?
That is a technicality in the physics books because if you stretch something, in this specific case, the spring is stretching downwards. So the delta x is technically a negative number. But the spring's force points upwards. So the negative is there to invert the force in relationship to the direction stretched. If the spring stretches down, the spring's force is going to push up.
To make the X positive.
To make the F positive. So working this from these numbers,
Well, yeah.
X would be a negative number because we've stretched it down.
Mm-hmm.
So negative times positive will give us positive spring force because the spring is exerting a force upwards on whatever is hanging from it. So that negative is a technicality because of the signs of vector multiplication.
So our answers technically are negative centimeters, because we know that it's going down.
If you were asked for displacement, correct. WebAssign doesn't seem to care though, because it's just asking distance stretched, but non-vector, simply how much longer is it. And as I said, all these examples are different variations and combinations of e-field stuff. So I'm actually going to make this assignment due Thursday. Just so that you guys will have time to make sure you've looked at them all. And if any more questions generate, we can address them on Thursday.
Is this what is due Thursday as well? Or just-
Yes, I'll make both of them due Thursday. Before we break for the day though, I at least want to address what Chapter 16 will be when we officially begin it. And that's going to be about capacitors. And the lab this week will also be about capacitors. We're still going to do the lab as planned. We're going to talk about how capacitors work, function in a circuit. To at least introduce the concept though, this situation is a capacitor, actually, because the definition of capacitor is usually one plate, usually one metal plate that is positively charged, that is parallel to a metal plate that is negatively charged. And the reason we would do that is because the positive plate is going to exert a field downward. The negative plate is also going to exert a field downward. So we build capacitors to create an environment where all the field lines just point in one straight direction, which you don't get in nature because single protons create a radial effect out of themselves. You don't get like a bunch of uniform lines in the same direction. You either get outward or inward radially. So this creates something that we don't normally find from single charges by themselves. And with the uniform field, we can do some very interesting things, like put charged particles in that field to see how they behave, and also store particles in those fields. So what we'll eventually come to be talking about is that a capacitor is basically the first type of battery humans ever invented. Occasionally accidentally. I guess humans didn't invent this scenario, but capacitors are functionally the earliest kind of battery. And that is what we'll get more into next time. For right now, focus on this assignment. Capacitors I will explain more in lab.
Also, for number 7, it's in centimeters, so do you have to convert it to centimeters or?
Formulas are designed for meters.
Right.
So whatever the formula gives you is meters, you know what that is. Have a good day, everyone.